Good morning, everyone. Like Carlos said, my name is Uriel Aguilar Gutierrez, and my project focused on the optimization of ethanol and acetone reagent ion concentrations in a chemical ionization mass spectrometer, also known as a CIMS, for improved detection of pyridine, which is a lot to say. But before we begin, I'd like to give a special thanks to my mentors, Bree, Max, Ellie, and then to the RECCS crew, Alicia, Carla, and Madison for all their support and for making all this possible. So thank you. So what exactly is a CIMS? So right here, I have a picture of the CIMS, and all it is a lab instrument that helps scientists identify and measure gases in the air. So through like the inlet right here, you would put in a gas, and the CIMS tells you you have this gas and this amount of it. And so one of the particular gases that I decided to measure is called pyridine. And the thing about pyridine is that it's toxic to humans, so that's kind of why I chose it. And some context about pyridine, it's released from industrial emissions and vehicle exhaust, tobacco smoke, and biomass burnings. And so the way the CIMS works is that it can only see the gases if they're charged. And so the way it does that is by using a chemical called the reagent ion. And so it mixes the gas with the reagent ion, and that's how it's able to identify whatever gas it is. And so the goal of my study was to see how changing the concentrations of two reagent ions, ethanol and acetone, affect the sensitivity of the CIMS to pyridine. So how does changing the amounts of these two reagents affect how well the CIMS can see pyridine? And the reason why we want to make the CIMS really sensitive to pyridine is because in the open air atmosphere, the concentration of pyridine is only about, it's only about 10 ppt, which means for every 1 trillion molecules of air, only 10 of those are pyridine. So pyridine is like a really small, like there's really small traces of it in the atmosphere. But why does this all even matter? Well, it matters for two reasons. The first of which is public health. So like I said, pyridine is a toxic gas, so we wouldn't want to be inhaling it. But the CIMS can also identify other gases that could also be harmful to humans, such as carbon monoxide and ammonia. And so maybe the results of the study could apply to those experiments. And then the other reason is climate change. So pyridine doesn't directly affect the climate, but acetone and reagents, or acetone and ethanol reagents could be used to identify other gases that do impact the climate. And so maybe a future scientist could take my results and apply it to their CIMS to optimize for those gases. So how did I go about my experiment? So down here I have a figure of the experiment setup. And so starting from the left, nitrogen gas is flowed through tubing, and it is split into a mass flow controller and a critical orifice. So the nitrogen that flows through the mass flow controller goes into the reagent ion bottle, and that's what carries like the reagent into the CIMS, so like acetone and ethanol. And then the nitrogen that flows into the critical orifice is what dilutes the reagent ion. So up here is a picture of a critical orifice. It's basically like a small cylinder with a small opening on one end and then like a larger opening on this end. And so depending on the size of the opening, that controls how much nitrogen flows through and like dilutes the reagent ion. So if I have a critical orifice with a bigger opening, more nitrogen is able to flow through and dilute the reagent ion. So I would have a smaller concentration. And so on the other hand, if I had a smaller opening, less nitrogen is able to flow through, which means I have a higher concentration of the reagent ion. And so what I did was I changed the critical orifice 3 to 4 times for both ethanol and acetone, and that's how I got the various concentrations. And then on the right is how I got pyridine into the CIMS. So similar to before, I used nitrogen that flowed, nitrogen that flowed over my pyridine source, and then into the calibration system and into the CIMS. And what the calibration system does, it allows me to control the concentration of pyridine going into the CIMS. And why that's important is so that I can create a graph called the calibration curve. So on the left, it has the signal of the CIMS. So it tells me like how much pyridine the CIMS can see. And on the x-axis, I have the concentration of pyridine. So as you can see, I used 4 different concentrations of pyridine in this experiment. And what that allowed me to do was fit a line through those points. And then depending on the slope, that's how sensitive the CIMS is to pyridine at that specific concentration. So for example, this one's at ethanol at 0.0518 millimoles per liter. So depending on the slope, so steeper slopes means that the CIMS is more sensitive at that concentration, and so that's kind of what we're looking for. So this is just one calibration curve, but I did this for a couple more concentrations and I got more calibration curves. And then I also did the same thing for acetone. So this one's at about 0.2 millimoles of acetone. And as you can see, this one has a much smaller slope of 1600 than that of ethanol. And then once again, I did this a couple more times for acetone. And so once I had all the various calibration curves and all the different slopes, I decided to make another plot to compare them all. So like the ethanol one has a slope of 6,000, and that's represented by that top left point right there. And then the other points are the other experiments that I did. And so what this plot showed me was that as I increased the concentration of ethanol, the sensitivity of the CIMS actually decreased, which was something like kind of interesting to me. But on the other hand, for acetone, as I increased the concentration of acetone, the sensitivity of the CIMS increased. And that's kind of what I expected, because I thought if there's more reagent ion, then there would be more for the gas to ionize with, so maybe the sensitivity would increase. But the importance of this is that it implies that they have different ionization mechanisms. So it's important for like scientists to know, like if they're going to use ethanol and acetone, to know like that they work in different ways, and so it's important for them to understand that. And then another thing that is important with this result is that in my lab, they've been primarily using ethanol at that first concentration. And so maybe in like future, maybe they should be using acetone at higher concentrations so that they get like more sensitive results. Which kind of makes me question like the previous results that they did, like maybe they weren't as sensitive, and so maybe moving forward they could use something that would work better for their experiments. And so in the future, I'd like to experiment in a more humid setting. So like in the lab, the pyridine that I'm putting into the CIMS is just like pure, or it's other stuff, but there's like no humidity in there, there's no water. And so what I learned was that acetone reacts with water more than ethanol does. And so I'm just thinking like if the acetone is reacting with the water, then maybe it won't be ionizing the gas, and maybe the results would be different. And then maybe in that case, ethanol would be a better reagent ion. Because like if you were to use the CIMS in the open air, there's always at least like 20% humidity. And so that's just something I like in the future. And then additionally, when I first started this experiment, or my research, I was testing the sensitivity of ammonia instead of pyridine, but our ammonia source was like running out, so that kind of skewed my results. So I just like to finish that experiment. And then the CIMS can identify multiple gases at the same time. So while I was measuring pyridine, I also measured another gas called trimethylamine. And I'm just curious to see if the results would be the same. We think they should, but we don't know for sure unless we actually analyze the data. And yeah, thanks for watching.